Great. Well, good day, everyone. It's great to see so many of you joining in for today's workshop from all over the world. Welcome to our online workshop, Tubular Ultrafiltration for Industrial Wastewater. When is the winning solution? My name is Elisabeth Kickert. I'm the Management Assistant at Berghoff Membranes, and I will be your host for this session today. In this upcoming 1.5 hours, you will learn practical proven strategies for successful tubular ultrafiltration for industrial wastewater from our Berghoff membrane experts. Welcome to our speakers, Dr. Elena Meabe and Adrian Gonzalez. Thank you for being here and explaining your expertise to all of us in this session. So before we start, just a few quick notes. This session, as you've noticed, is being recorded. So by participating, you agree to the recording and the processing of your data in accordance with our privacy policy. Your camera and sound should be already automatically off and on mute. We will start with a short introduction of our company, followed by the presentations of Elena and Adrian. And then we will finish with questions and answers session at the end. Feel free to submit your questions in the Q&A chat throughout the session. So again, we will answer after the last presentation. Okay, so why tubular ultrafiltration matters now? So our motivation, we have a few bullet points which we will go through, is increasing the presence of highly challenging industrial wastewaters and process streams, growing limitations of conventional treatment technologies, rising demand for robust and high-performance filtration solutions, a strong push towards water reuse and circular water management, and the need to create awareness of effective technologies such as tubular ultrafiltration. Our goals are to present the principles of tubular ultrafiltration technology, highlight its key advantages, explain where and why to apply tubular ultrafiltration in industrial contexts, connect application needs with technology strengths, share practical design criteria and operational guidelines, and provide insight based on real industrial experience and case studies. Berghoff Membranes, we are a leading manufacturer of tubular UF membranes for the filtration and separation of industrial wastewater and process streams, including industries like dairy, food and beverage, landfills, chemical, pharmaceutical, biogas plants, oil and gas, and many others. With more than 50 years of experience and over 2,500 installed systems across the globe, we pride ourselves on the robustness, flexibility, energy efficiency, and superior quality of its external filtration membranes and solutions. We're located at 4 sites: Germany, our manufacturing location, offices in the Netherlands, Singapore, and Spain. Our core technology is MBR, ANMBR, and direct filtration. The core technology involves membranes which are available in different tube diameters, materials, and cutoffs. Multiple features are standard, backwashable, and chemical resistant. Pilot modules available in different sizes, screening versus scalable, and industrial modules available in different diameters and lengths up to 71 square meters unitary service. Our B-Care service and support program involves application analysis. It's to develop new and optimize our customers' applications. Pilot testing, on-site testing with our containerized pilot unit, ensuring the system design delivers optimal treatment. Engineering and commissioning, our engineering package and either on-site or remote support for starting the system, and technical after-sales support, which is a range of services and technical support to make sure the system is always performing with minimal maintenance. So let's get into detail and rethink the treatment of industrial wastewater and why tubular ultrafiltration wins. So it's my pleasure to introduce you to our first speaker, Dr. Elena Meabe. Elena is a manager of the Knowledge Center at Berghoff Membranes. Elena is chemical engineer and holds a master degree in environmental engineering. She's also a doctor in industrial engineering with her PhD research work focused on membrane bioreactor technology and the monitoring of membrane performance. To this day, she possesses 18 years of experience in filtration technology, mainly dealing with external tubular membranes. She has a deep insight into the membrane technology for the industrial wastewater treatment market and will now guide us through key insights on today's topic. So, Elena, thank you for being here, and I'll pass it on to you now. The floor is yours.
Okay. So, hello, good afternoon. I will activate this. So I think now you can see my screen and everything is working well. Let me just do one thing. Okay, I think everything is going on. Thanks, Elizabeth, a lot for your introduction. And well, good day, everyone, and thank you for joining this workshop today. In this workshop, we are going to focus on tubular ultrafiltration for industrial wastewater, and more important, on when it is actually the right solution. So the goal is not only to promote tubular ultrafiltration as the answer to everything, but to help identify the situations where it adds real value. This session is designed to be practical and decision-oriented. It covers some of the basics because, well, probably many of the attendees already know about this technology, but for others, we know that this is like the first introduction and we really need or want them to know about the basis of this tubular ultrafiltration technology. So for this, we will start with the fundamentals of tubular ultrafiltration and then move into the main industrial wastewater challenges. We will also look at general design guidelines, operation, and we will finish with typical applications and specific case studies. So the intention is to connect membrane theory with real plant decisions, understanding not just how tubular ultrafiltration works, but why it is chosen in some cases and not in others. So, well, industrial wastewater is fundamentally different from municipal wastewater. We are often dealing with high solids concentrations, oils, refractory organics, streams that can vary significantly depending on production cycles, batch operations, CIP events. So this variability creates shock loads that conventional systems often struggle to handle. At the same time, discharge requirements are becoming stricter, water reuse is gaining importance, and many plants still face space and uptime limitations. So before selecting any technology, it is essential to understand the real complexity of the wastewater and the operational constraints around it. So, well, the big question becomes, when does tubular ultrafiltration make sense? This is really about application fit, right? It is finding the right technology for the right challenge. And this is what we are going to explore in the next slides. So, well, the basis. Tubular ultrafiltration is defined by a few essential characteristics, okay? First, the channels, the membrane tubes, are relatively large, which allows the system to handle feeds with high suspended solids or viscosity. Second, filtration takes place in an inside-out mode, where the feed passes through the tube and the permeate crosses the membrane wall. And third, the system operates in crossflow, meaning that part of the liquid is continuously circulated to create a shear at the membrane surface. So this shear is key because it controls fouling and keeps filtration stable over time. This cross-flow concept is one of the main reasons why tubular ultrafiltration is considered robust for difficult industrial streams. Apart from this, one of the strengths of tubular ultrafiltration is the flexibility across many different process setups. Okay, it can be connected to a biological process as part of a membrane bioreactor or anaerobic membrane bioreactor. It can be coupled to a chemical precipitation process for removing hardness, silica, heavy metals, or other dissolved pollutants, or it can be used as a standalone ultrafiltration step for separation, concentration, polishing, recovery applications. And well, the application range in terms of industries is also very broad, from dairy, food and beverage, chemicals, tanneries, leachate, digestate, waste management, many of them. So let's say that this is not a niche technology for one sector, but a platform technology for complex liquid streams. Here in this slide, you can see that tubular ultrafiltration becomes a strong option under specific conditions, okay? So, for example, when the wastewater has a high fouling tendency, when available space is limited, when the feed conditions fluctuate strongly, or when maintenance needs to be simple and with minimum downtime. In this kind of scenarios is when tubular ultrafiltration excels and delivers its really advantages. It is also important to say that tubular ultrafiltration is not always the lowest cost option from a pure CapEx perspective, okay? But in many challenging industrial cases, it becomes the most reliable and practical solution because it tolerates difficult feeds better and also provides more stable operation. So well, to make this more concrete, here are some examples highlighting how tubular ultrafiltration maximizes efficiency per square meter. And this does not only refer to the ultrafiltration system footprint, but to the global treatment process. First, of course, ultrafiltration skids are modular and highly compact. But what is more important is that they offer exceptional design flexibility for fitting into the available space. Okay, this can be critical in certain projects. Here, for example, you see some pictures. The first one is the ultrafiltration system located over the bioreactor. The second one is as an ultrafiltration system inside a container. And in the third one, for example, you see that the three ultrafiltration systems are placed like in a platform over the tanks in a very low height area. So this flexibility for installation can be really a difference for addressing certain projects. Second example, this is small production, okay? So tubular ultrafiltration enables direct reuse of the MBR permate in the steeping process, in the manufacturing process, and still maintains a very, very compact footprint. As a rough estimation, we can consider that the required area for the ultrafiltration system can be up to 10 times smaller than that of a conventional settling system. And moreover, as you may know, the bioreactor is much smaller. And in this case, there is an important advantage is that the MBR effluent is directly reused without requiring further polishing. So there is no any additional treatment before reusing. And then in the third case, This is a distillery application, a high strength wastewater with COD even above 30 grams per liter, which is treated with anaerobic MBR. So in this way, energy is produced for the factory in this case. This system achieves COD removal higher than 95%, and this again enables direct discharge into the sea. Well, I can tell you that as far as I know, there is no other anaerobic technology apart from the anaerobic MBR, which is able to do this in just a one-step treatment. Okay, so now we are going to move from why to how. So up to this point, we have focused on why tubular ultrafiltration can be the right choice. Now we move to the next step, which is how to design and integrate ultrafiltration properly into the treatment plant. This slide shows a typical feed and bleed configuration, which is the most common when designing tubular ultrafiltration systems. So in this arrangement, there are two pumps, feed and recirculation, and there is a continuous recirculation inside the membrane loop. This is to maintain the cross-flow velocity inside the membranes. Moreover, the feed pump introduces certain flow to the recirculation loop. Part of this flow is obtained as permeate, and the rest is the concentrate or retentate stream. So the ultrafiltration modules are usually installed in series, usually up to 6 or 8, depending on the design cross-flow velocity. And also, we always recommend installing a safety strainer after the feed pump for protecting the membranes. And finally, the only thing that you need to install is the CIP flushing tank for membrane flushing and cleaning. So well, when designing and operating a tubular ultrafiltration system, a few parameters are especially important. This includes transmembrane pressure, pressure drop, cross-flow velocity, recovery, concentration factor, permeate flush, permeability. But what matters is not only each parameter individually, but also how they interact. For example, increasing flux may improve productivity, but it can also accelerate fouling. Or increasing cross-flow improves fouling control, but it also affects energy demand. So optimization is always a balance between productivity, liability, stability, and operating cost. System design. This is essentially about connecting process requirements to equipment selection. So the main design parameter is the permeate flux. This value is determined based on background experience or pilot trials, depending on each case. And then, based on flux, we need to define membrane area. And also, depending on the application and the wastewater characteristics, we select the membrane type, diameter, cutoff, module configuration, for example, backwashable or chemical resistant modules. Once we have this selected, we need to select the most adequate module size, diameter, and length. As a general approach, we try to select the smallest module, which gives a reasonable number of modules in series. This is generally more energy efficient. I mean, it is better to install 4 modules in series of certain size than installing just 2 modules in series with a bigger diameter. All these kind of decisions, of course, we can or we always support our partners and customers for finding the best solution for each specific case. Then, because of the project capacity, we need to install more than one skid, we can go for single loop or double loop. One double loop is like 2 membrane lines, which are fed with the same recirculation pump. And also the permeate lines are interconnected. Double loop is better in general in terms of capex, but it can reduce flexibility, okay? go like this. Okay. On top of that, the pump sizing is critical. For the feed pump, the flow is based on the chosen concentration factor, which is the ratio between the feed and the retentate flow. And concentration factor sets the solids concentration inside the loop. Okay, for example, concentration factor of 1.2 means that MLSS will get 20% concentrated in the ultrafiltration loop. And then for selecting the feed pressure, the feed pump pressure, we need to consider the retentate pressure, which is the pressure at the outlet of the last module, and also the pressure drop in the safety strainer. Then recirculation pump. The recirculation flow depends on the target cross-flow velocity. And the recirculation pump pressure is the pressure drop along the modules, which is also dependent on the cross-flow velocity. And finally, a dedicated CIP pump is installed in some cases. For example, when the feed pump is submersible, or in many cases when the feed pump is not able to provide the flow corresponding to 1 meter per second cross-flow velocity inside the tubes. This is the requirement that we have for the membrane flushing. And then, in addition to membrane or module design itself, the system concept can also be adapted depending on the customer's priorities or the project's requirements. Here, the VSmart range illustrates different approaches. Okay, for example, there are solutions focused on lower capex, or increase automation, or lower OPEX. So the level of automation, permit flow control, backwash capability, remote access, all these can vary depending on the selected concept. For me, the point here is that not every application needs the same level of complexity. So the system should match the technical demands of the process and also the operational expectations of the plant. So, well, operation mode. So, tubular ultrafiltration is not limited to filtration alone. In addition to the filtration step, the system must also include other operation modes, such as the flushing, CIP, conservation, and in some configurations, backwash or chemically enhanced backwash. Each of these modes has a specific role. Filtration produces permeate, flushing removes residual solids or pollutants when the system is stopped or before and after a CIP cleaning, or flushing can be also implemented periodically to control fouling. CIP restores permeability with chemicals, and conservation protects the membranes during shutdown periods. Then for flushing, UF permit can often be used, but for CIP, we always recommend to use tap water or damming water. And moreover, when tap water is used, it should have low hardness, okay, for avoiding scaling during the alkaline cleaning. So now let's focus on the process integration around the UF. First, even though tubular ultrafiltration is very robust, it requires pretreatment. Pretreatment is still important, okay? So typically some form of screening is required to protect the system from big solids or hairs, fibers, etc. As a standard, rotary drums with 0.75 or 0.8 millimeter mesh size are used. The screen should be square mesh or perforated plate. Okay, slots are not recommended as they only provide the required sizing in one dimension. Then, if hairs and fibers are present, a finer mesh is usually recommended in the range of 300 microns or even less. And for these filters or vibrator screens can be used. Then, if fats, oil, and grease are present, additional pretreatment might be necessary in some cases. If there is free oil, we recommend removing it with simple equipment such as an oil trap or oil skimmers. Regarding emulsified oil, okay, tubular UF membranes can cope with it. In fact, we have several projects dealing with oil-water separation where the membranes are facing really high concentration of oil and grease, even more than 100 grams per liter. So this is not a problem for tubular ultrafiltration. There is a special case, which is the aerobic MBR, where DAF pretreatment is often installed when oil and grease is present. More than by membrane limitations, this is related to the biological reactor, where oxygen transfer, biological activity can be affected by the oil and grease, and also some kind of foaming or greasy superficial layer can appear on the bioreactor. Then, from pretreatment, we have the safety strainer in the UF system. We usually recommend a mesh size of 1 millimeter, and then strainer cleaning can be manual or automatic. This depends on the case or on the customer's preference. Important, safety strainer mesh will be always bigger than pre-treatment mesh. This is because pre-screening has the function of structurally removing debris from the incoming water. The strainers in the fifth line of the ultrafiltration only have a security function. So this is important. Safety strainer mesh always bigger than the pre-treatment. Finally, beyond the ultrafiltration system itself, proper integration into the overall process is essential. So upstream, the interaction with the feed tank or bioreactor must be carefully considered. For example, liquid height can influence pressure conditions in the ultrafiltration. So with tall tanks, feed pressure is usually available, but retentate pressure will increase. So this means that in some cases, even people install retentate pump instead of feed pump. Or when retentate pressure increases, the maximum number of modules in series can also be affected. So this fact needs to be considered when designing a system. We also need to think, for example, about how the concentrator reject stream is handled in direct filtration applications. One option is batch or semi-batch operation, or we can extract the reject from the retentate stream, from the ultrafiltration loop. So in this case, again, depending on the recovery, the system can operate with direct reject or with partial recirculation of the feed, to the feed tank and semi-continuous reject. Then, downstream side. The key question is the required permeate pressure. Long piping distances or elevation differences or additional equipment can create pressure losses in the permeate pipe. So, as a rule of thumb, our consideration is that if the required permeate pressure exceeds about 0.5 bar, it is often better to include a dedicated permeate tank with a transfer pump. Again, this can be customized based on each project, and we can also support on finding the best solution for each project. And finally, when it comes to operation and maintenance, okay, monitoring the right parameters is critical, as in any system. So we usually design ultrafiltration systems with permeate flow control. Okay, it can be done manually or automatic, but we recommend this mode of operation in terms of stability. So well, when you operate in a constant permeate flow, transmembrane pressure is the key indicator of fouling development over time. On the other hand, pressure drop across the modules needs to be also monitored, as it can indicate changes in viscosity, but also any potential clogging issues. So pressure drop in the loop is also an important parameter to monitor. Then chemical cleaning. This is also an essential part of operation, okay, because it needs to restore the functionality of the membranes. As you may know, standard CIP procedures typically combine alkaline oxidant and acid cleaning to remove organic and inorganic fouling. And in some cases, special chemicals such as enzymatic cleaners or degreasing boosters are highly efficient for certain circumstances, okay? Then we have mechanical cleaning. Well, first of all, it is important to distinguish between fouling and clogging, okay? Fouling is expected and happens in any membrane installation. You apply the CIP cleaning and the system is performing again and at its maximum, let's say. But clogging, which is the mechanical blocking of the membranes, is something that should not happen and usually indicates a process or pre-treatment issue, okay? Some kind of operation which is not performing well. So then clogging should not happen. In any case, if this happens for any unexpected reason, deposits can be removed physically with mechanical cleaning. We also have procedures for the operators to inspect the membranes if required. And in the case that for some reason one membrane tube gets damaged, the module can be repaired with a simple procedure. So you can still continue using the module without any problem. And finally, as part of our services, we also offer the option to carry out membrane autopsy studies, which is something quite, well, usually demanded by some operators. Basically, membrane autopsy help better understanding the fouling mechanism and also, which is really important, optimize cleaning strategies. So, well, then with this, I reach the end of my presentation. I would like to thank you for your attention. I hope that, well, this session has helped you clarifying when tubular ultrafiltration is the right solution and how to approach from the basis its design and operation. And well, now my colleague Adrian will go from theory to practice and will focus on typical scenarios and real case studies. Okay, many thanks, and well, will see you later again at the Q&A session. Many thanks.
Thank you, Elena. I will take over shortly before Adrian will present. There we go. All right. Thank you, Elena, for sharing your knowledge in this presentation. So before we continue, just a small reminder that we will discuss questions after the following presentations of Adrian. You can submit your questions in the Q&A if you'd like already, and then we will process them after. So now it's my pleasure to introduce you to our second speaker, Adrian Gonzalez. Adrian is an environmental engineer. Oh. There we go. We were going a bit too quick. Adrian is an environmental engineer with a master's degree in water technology. He has a wide experience in industrial water treatment projects. During his time at Berghoff Membranes, he was actively involved in the worldwide design and engineering of ultrafiltration installations for several industrial applications. Adrian is responsible for the European and African markets, combining technical expertise with commercial and strategic responsibility. So thank you, Adrian, for being here today. If you're ready, then I will pass it on to you now.
Thank you, Elizabeth, for the kind words. I will share my screen. Good. I think now everybody should be able to see the presentation. So thank you, Elizabeth, for the introduction, and good afternoon, good morning, good day, everybody. It's a pleasure to see some familiar faces and some new faces in today's presentation. For this second part of the workshop, I will try to focus a bit more on the practical side from what Elena has described previously. So just to, with some examples to show where, which cases ultrafiltration tubular membranes is the best fit solution and can be the winning solution compared with conventional treatment, conventional submerged systems. So without further ado, I will start. First, I will start just with two slides of a bit more theoretical before jumping into the practical case. So when we look into a project where we are thinking on implementing tubular systems, we look at different selection criteria and different project requirements. If one or two, let's say, of these project requirements is fitting, then we should start thinking on using external tubular membranes. So just to give some ideas or some examples. So for instance, when we look at the wastewater characteristics, and in that case, in industrial waters, which have either high solids, high oil and grease, high variability, high falling risk, then the use of the external system is going to give a robust system capable to handle this falling potential. We can play with the high cross-flow velocity, but also play with the cross-flow velocity to adapt to these also challenging and variable conditions that the industrial wastewater normally possess. If we then, for instance, look into industrials where the effluent quality or they are looking into permeate reuse or a permeate that has low solids and is stable. So in those cases, also the impact of applying external membranes, what we are going to be able to achieve is free of solids, so low turbidity. And on top of that, it's going to have a constant permeate quality, even if the pretreatment is not working as well as it should. Space availability. I think Elena showed already a nice examples when limited footprint or other restriction conditions are in place. We can present a flexible and modular system. So you can think on skids on top of a bioreactor, on top of a platform, on the basement of a building. So always with these modular systems that can adapt to these space constraints. OpEx, operation and maintenance. For sure, it's something that we and your clients are looking into these days. And by that, we are also thinking on the easiness of operation of the system, on if there is available of operators on site to operate the systems. So again, the impact of using external tubular membranes is going to give a simpler operation with a long membrane lifetime. And there are many other selection criteria, project requirements that might lead to this implementation of tubular as the winning solution compared with conventional treatment. But if one or two are present, let's say, then it makes sense to start thinking on external. In terms of industries, these are used to highlight a bit the challenging industries where normal external membranes are going to be placed. It's not limited to this. There might be others that are not on this list, but generally when there are variable streams with heavy solids, difficult contaminants, toxic, and then other technologies struggle to operate, then it's again when it makes sense to use external tubular. So just to give some ideas of industries that have a high advantage. For instance, dairy. Certainly, we have many references, or food and beverage. Thinking on brewery, distilleries, wineries, meat production, slaughterhouses. Are waters that generally have high organics, high organic matter, oil and grease, high salinity. So those are conditions where the robustness of tubular membranes is going to be then highlighted. Then landfill leachate, biogas plants. In biogas plants, we can think on the treatment of digestate or the anaerobic system, so anaerobic MBRs. So definitely, for sure, those are the most complex waters that we can think of, are waters with variability of the influent flows, variability also on the composition, high levels of contaminants. So again, tough and challenging applications. Same level perhaps as landfill and leachate, we can think on hazard waste, where there are streams coming from different natures. So from chemical waste, paint, waters that have high levels of contaminant and toxic components. Not to stop here, but you can also think on pharma, cosmetics, laundries, industries where they operate in batches, where different products are being produced, which also means that there is variability on the composition of these waters that is going to affect the treatment that it is being applied. So we have now a bit the idea of what is the selection criteria or the project requirements where we need to start thinking on applying external membranes. But perhaps it's now good to see some case studies, examples where this has been the winning solution. First scenario, however, I would like to focus slightly still on a theoretical point of view. As Elena introduced briefly, and as you know, membranes or external tubular membranes can be applied directly in contact with the wastewater, or can be applied in combination with a biological system, either if it's aerobic as an MBR, or it is anaerobic as with the absence of oxygens. When membranes are applied as direct, in contact with direct wastewater, then we can think of many different industries. Cosmetics, for instance, to reduce the volume of waste that is being generated to reduce the cost of discharge, or for further processing in digestate to remove the high suspended solids present in these biogas plants. From the point of view of MBR and anaerobic MBR, tubular membranes are going to be a strong fit, especially in those systems where the sludge filterability is low and the operation conditions are especially demanding. So you can think on waters that have organic shocks, refractory COD, high salinity, inhibitor components, or for instance, the biomass is simply releasing EPS, which is deteriorating the quality of the sludge. So this is typically something that can happen in leachate, digestate, tanneries, rendering, hazard waste type of industries. In anaerobic, actually we encounter also again challenging operational conditions, and in those cases, actually only external tubular membranes is going to be the right fit. Those cases generally, the biomass also shows poor filterability, is rich in biopolymers, has colloidal fraction. So in those cases, again, the external is going to be the only solution. And like Elena said, it's going to be the solution in being able to treat the stream in only one step. Let's show some case scenarios now, really from the practical point of view, which I think is really the most relevant sometimes. First, when you can think on, or first case, why does it make sense to reconvert the system, for instance, to an MBR? So you can think, for instance, of a client that has a SBR or a conventional activated sludge system. If by reconverting this treatment, which might be not up to date, we can improve directly the biological performance and the effluent quality. The effluent quality, for instance, can be directly already for reuse strategies. So we are not only improving the quality of the permit, but we can also, for instance, expand the hydraulic capacity and load capacity of the system if the system is not capable to load this variable or increase load that the client might be facing. Actually, the implementation of tubular membranes is going to be fast and flexible. This can be integrated in a simple skid installation, minimal disruption, producing the civil works. And in cases, for instance, of SBR systems, the aeration is already ready for this reconversion, because in SBR systems, aeration is normally designed for a shorter period of time, while expanded to 24 hours, there is enough capacity for doing this. To put all these works into a case study. In this case, it's a chicken slaughterhouse in a project in Belgium, project executed by our partner, Aqua. In this case, the client had a problem, and that was they were facing an increase in capacity, and they had a water cost, let's say, that they needed to look into what were the options to reduce this water cost. For this, the current system, the current SBR system they had implemented was then not enough. Solution that Aqua presented for this case was a simple reconversion of the SVR system, for which the aeration was already ready for this reconversion. So it simply went to 24-hour per day operation, increasing the MLSS. And with this plus further treatment with reverse osmosis, they were able to face this increased capacity. So overall, in this case, the client is able to treat with the MBR system about 50 cubes per hour, from which 20 cubes per hour are already reused directly for lower quality demand. So for instance, for floor cleaning, truck cleaning. The 30 cubes per hour remaining from this pyramid were further processed with a reverse osmosis treatment. And from this reverse osmosis treatment, 20 cubic meters per hour were again reduced within the process, and in this case, even with direct contact applications. The discharge of the reverse osmosis could be directly to seawater with even a higher quality than the existing previous treatment plan. So with this simple solution of system that you have here in the picture, the client was able first to face this increased load capacity, to reduce the water consumption from the tap, which was costing the client €2 per cubic meter in this case. Actually, the quality of the reverse osmosis was even higher than the tap water, so avoiding softening, and the temperature was also higher, so also avoiding heating of the water. Let's go now for a second practical scenario, or third scenario, and in this case we are going to focus on waters with high solids. Normally high solids also means high viscosity, it's correlated, and poor filterability. Those are systems where normally conventional membrane systems are going to fail to perform. You will need to focus on a system that is robust enough to handle this high concentration of MLSS, suspended solids, high viscosity. For this, actually, we've developed a new series of membranes with a larger geometry, and in this case, 12.7 millimeters. These allow us to work with these high concentrations and avoid the risk of clogging. So you can think on projects, for instance, on diastase treatment or anaerobic systems where these concentrations are very high. This, in combination with the already high cross-flow velocities that we can apply with our technology, we can help reduce the cake buildup or falling while sustaining a higher flux over a period of time. To put this into a nice case study, and I find this case study also very interesting from the very beginning. In this case, it's a client where the main focus was on the first instance to simply recover the PVC powder. This is a client that was producing PVC, and they were generating 720 cubes per day of water containing this PVC powder. It's also a very nice case study because from the beginning in this project there was a piloting to prove the client this was the right solution. So also highlights that sometimes the best way for you to prove your clients what is the right solution, piloting might be a very important step. After this piloting, we executed the project, and the project consisted mainly on an ultrafiltration system that was able to concentrate this PVC powder. So from this 720 cubic meters per day, we were able to recover 90%. The reject, which is what the membranes were facing on nominal conditions, was up to 40 grams per liter. This reject was the main purpose for this client, and was further sent then to a filter press to concentrate up to 50% in dry matter. The nice part actually of these projects is that also later on, towards the final stages, they also released that the quality of the permit that they were achieving with the ultrafiltration was high enough to also be reused again within the factory. So in that case, they avoided also to have an additional reverse osmosis or softening of the tap water. So simple implementation, being able to handle high concentrations of solids. Let's go now to a second scenario. And in this case, we are going to focus on when flexibility is the real value added by our technology. In that cases, tubular ultrafiltration system offers a modular solution, and especially in industrial, where the conditions are uncertain today or are likely going to change over time. And this is actually, I'm sure you have experienced, often the reality in industrial wastewater treatment. So instead of fixing a design for today, we can start looking into a system that is future-proof towards potential expansions of capacity, site requirements, or the legislation is changing. So in a way, we are also helping clients to align investment with different project phases. So the capital or the capex, let's say, is deployed also over time. So we can think of parallel lines, pre-assembled units that can be easily deployed on site and later on move to another site. So overall, is able to offer high flexibility. And to highlight a case study in which this is clearly exemplified. In this case, we are talking about a landfill leachate in France, Saint-Pierre, a landfill that it is active since 2004, and a project which was executed by our partner OBIF. In 2009 was the first stage in which OBIF implemented a membrane bioreactor, some biological system with ultrafiltrations, and then this was coupled with an nanofiltration. Just 5 years after this initial investment, there was already an increase of 50% of the capacity. 5 years later, or in the next 5 years, there was then not related to the ultrafiltration, but to the complete treatment, there was an upgrade in the sludge, the watering. And then in 2019, actually, the restrictions for discharge into marine also increased, which also meant that the OBIF had to also increase the polishing required for this system. Up to last year, in which there was again a second expansion capacity. So I'm sure you're familiar with this, but you can see in this case, and especially in landfill leachates, also where there is variability on the influent flows, but also of the quality over a period of 20 years, there are completely changes. So by implementing these flexible and modular solutions, we can adapt over time, and easily client will see the benefit into potential expansions or changes on their process over a period of a year or a few years. If we move to scenario number 5, and for this we will use dairy as example of managing variability, tolerance to high oil and grease, and minimization of scaling issues. A bit the same as was introduced in the previous case scenario, but in the industry overall and also in the dairy, in particular, also the quality does not stay constant. So there are large volumes that might come from different sources. So you can think of raw materials production, so spilling of trucks, losses loading trucks, cleaning, sanitizing, waste processing. So there are high variability of composition that can affect the quality of the treatment. In those cases where the pretreatment it is not working well, is not able to handle these swings of quality, then ultrafiltration can provide a safeguard. And despite those variability, for instance, on previous DAF treatment to deal with the oil and grease, those cases, the ultrafiltration system is still gonna let's say the performance of the ultrafiltration is still gonna remain stable. In dairy, for instance, we are not only talking about oil and grease, but we are also talking about hardness, which is always high in this type of applications. And in those cases, submerged, for instance, submerged systems are going to be more exposed towards scaling, cave buildup, biomineralization, while in contrast for external systems, where we use cross-flow technology, as Elena has introduced, rather than aeration to control this deposition, we can reduce the formation of cake on the membrane layer. To exemplify a case of working with these high concentrations of solid oil and grease, and in the case of the dairy industry. In this case, we focus in a project in the States, and it's the end client is a client which was producing butter and butter derivatives, for which they were generating around 2,000 cubic meters per day of wastewater. This case, the client had also already an existing treatment, which consisted of a DAF unit plus a conventional activated sludge. This system presented at that moment several problems. So from one side, there was a high consumption of chemicals in the DAF system, also generating of high volumes of sludge, which needed to be then disposed or to be further treated. Plus, the high variability and swings of the DAS system made that the quality of the conventional activated sludge was also not good enough. So in this case, in a first phase, what we did together with our partner was simply to reconvert this conventional activated sludge into a MBR system. With this, we were able to handle this variability of the pretreatment and still achieving a stable and constant permeate quality, which is, after all, much more operator friendly also. The permeate from this MBR was actually further sent to a reverse osmosis, and in that case, the client could also reduce again the reverse osmosis permeate within the factory, so for the cooling towers, the steam generation, and other parts of the process. The nice part of this project is that in a second phase, which was around 5 years after the initial reconversion towards an MBR system, there was a segregation of the different lines of waste within the plant. So we had the low strength wastewater and the high strength wastewater. What we did was then the high strength wastewater was then segregated or sent then to a new system, a new anaerobic bioreactor system. This anaerobic system of 3,900 cubic meters per day could treat in only 40% of the total flow, 70% of the organic load, so loads that could reach up to 40 grams per liter of the influent. Actually, the quality also achieved by the anaerobic, you can see it on the screen on nominal conditions below 300 ppm, so it's a removal efficiency in only one step, very high for an anaerobic system. Of course, with an anaerobic system, they could also produce biogas, which could be converted into electricity. So overall, in this project, in this dairy project, the client went from a conventional system to an MBR and anaerobic MBR system, saving up to $150,000 per month in total. Sorry, I will present now the sixth and final scenario, and in this case, focus on limited space and high concentrations of solids as the selection criteria or project requirements for this particular case. And for that, I will focus also on the reverse osmosis brine recovery or ZLD type of projects. Those projects, there is a combination of a chemical precipitation at high pH before the ultrafiltration. So the dissolved components can be converted into solids or can be precipitated directly later in only one step with ultrafiltration. Due to the high pH in this chemical precipitation, and for this reason, we developed also a new product line that is capable of working in nominal conditions up to a pH of 12. In this case, compare also with conventional treatments, what we are able to do with ultrafiltration is to tolerate these high solids while removing a full removal of suspended solids in only one step. So conventional treatment, you will have the chemical precipitation, which most commonly will also use flocculants, coagulants, while in our case, we can rely only on common chemicals like lime, soda ash. So we are already reducing 20-30% of the chemical consumption, so already reducing on capex. And then only in one step directly after this chemical precipitation, we go to the ultrafiltration. So there is no need for sedimentation, plus multimedia, plus hollow fiber. So this will present already the second advantage in those cases, because we can reduce in only one step around 40-60% of the footprint. A much more simple system. To show a case study for reverse osmosis recovery, you will see in this case, a project in China. The end user was facing stringent water requirements for water reuse, actually, and they were looking for the most cost-effective solutions to treat the reverse osmosis concentrate and focus on a ZLD project. And I think that this picture already describes one of the key advantages. The picture that we have here on the screen, which is a double loop system, it's only this system, only this footprint is treating 3,000 cubic meters per day. So in only one step, we are able to remove 100% of the suspended solids that are in the previous chemical process. So a high footprint advantage for this client. Plus, a bit as introduced just before, they could save in the chemicals used in the chemical precipitation, so 20 to 30% of the chemicals were saved compared with conventional approach. And we are still working at high concentrations of solids. 20, 30 grams per liter is what the ultrafiltration system was seeing in nominal conditions, actually with very high fluxes. Actually, this is a type of application that today more and more industries are deploying towards zero liquid discharge policies. So this actually brings me to the end of the second part of the workshop. But before I close this part of the presentation, I would just like to highlight the key takeaways for this part of the presentation. So you should see tubular ultrafiltration as a powerful tool for industrial water. So the more complex the water, or the tougher the cases, the better it's going to suit external system. So the value is then highlighted by handling these high concentrations of solids, variable streams, where other technologies are going to struggle to operate. You should not be seeing tubular external systems as just the default choice, but more a strategic solution where then the robustness, the flexibility, the modularity, stability of the permeate quality outweighs then the concerns of capex and opex. So overall, having a solution that it is cost efficient and waterproof, future proof. I think I leave the grounds to Elizabeth now. You are muted, Elizabeth.
Here we are. Perfect. Thank you, Adrian, for reminding me. Thank you for your presentation. I'm sure it was very insightful for everyone attending today. We will now move on to the questions and answers session. So as a reminder, feel free to submit your questions in the chat. And Elena, Adrian, if you can join as well and turn on your camera, and then let's see. Okay, so we have, we have a couple of questions, so that's good. The first one is for Elena. Won't the polymer carry-off affect the UF if a DAF is used ahead of the membranes?
Okay, well, we have many references and projects running like this with a DAF pretreatment. On the one hand, it is true that polymers added to the DAF, in the case of MBR, for example, they are getting some kind of diluted over the bioreactor. And apart from this, especially the cross-flow operation of the tubular ultrafiltration allows to really be robust under this kind of potential foulant components. Having said this, we have seen cases where there has been any kind of operational issue which has led to overdosing of chemicals, where yes, you can see a decrease in the permeability of the activated sludge in the case of an MBR, but there is not like a huge impact on the membranes. And if this is the case, you can apply a chemical cleaning and everything is solved quite easily. I would like to highlight that In some of these scenarios, our experience is that applying some types of enzymatic cleaners is helping for restoring the functionality of the membranes.
Okay, perfect. Thank you. Okay, so the next question, Elena, is also for you. Is there no relaxation step like for submerged membranes for this type of membrane?
Okay, this is yes and no. So let's say that in conventional cross-flow operation, it is what we call B-Smart performance. There is not a need for implementing any kind of relaxation of backwash sequence. It is the cross-flow velocity that allows us to minimize fouling and operate with really high fluxes of, I don't know, 80, 90, even more than 100 LMH. On the other hand, we have what we call B-Smart Eco, which is an approach for reducing the energy consumption and are systems designed to operate with lower cross-flow velocity. When this is the case, we do have to implement relaxation and or backwash sequences, or also chemical enhanced backwash. So conclusion, relaxation backwash is only when we are designing in a low cross-flow velocity condition, which can be something like less than 2 meters per second cross-flow velocity in the membranes.
Great. Okay, thank you. There's another question for Adrian. Is it possible to treat reverse osmosis concentrate through tubular ultrafiltration? And do you have any real cases where this has been done?
Yes, we actually have many case studies, just as the one I show for the soda ash manufacturing in China, where they were explicitly treating reverse osmosis, but we have also in power plants for the treatment of also the cool from the cooling towers, the blow down from the cooling towers, but also nanofiltration, brine, reverse osmosis brine from landfill leachate. So it's overall a technology that we have in our portfolio. For these systems, a bit as I mentioned before, since the pH, one of the importance is that the pH of the previous chemical precipitation, especially for removal of the hardness, is at a pH higher than of 10. For that, we need to think on the CR membranes to be applied in those cases.
Okay. There's another question for you, Adrian. What's the average membrane pore size?
For I would say for 90% of the cases, the standard 30 nanometers is going to be applied, especially for membrane bioreactors, either aerobic or anaerobic. The main focus there is to removal of the suspended solids or the biomass. So with that, 30 nanometers is going to be highly applied. You will be able to remove suspended solids and some of the colloidal matter. If we go also for direct filtration applications, most of the time also 30 nanometer is going to be enough if the focus is again on removal of the solids or as a pre-treatment before a reverse osmosis or for the treatment. Nevertheless, there are specific cases where other pore sizes are required. So we can think then on 100 kilodalton for removal of specific protein components, but also 50, 15, 5 kilodalton. Just to summarize, however, the average membrane pore size is going to be 30 nanometer.
Okay. All right. Thank you. Another question for Adrian. What is the typical biomass concentration in tubular MBRs?
In these cases, for tubular MBR or external tubular MBR, and for aerobic systems at least, we can think of a concentration between 8 to 12 grams per liter. We have references also at higher concentration, 15, 20 grams per liter, for instance, in diastates where the concentration of influent concentrations of suspended solids is high enough. That also requires that the biological reactor is also designed high concentration. But in the end, it's also to look the balance between ultrafiltration and biological reactor. The higher the concentration also has their own downsides. into the oxygen transfer in the biological reactor. So just to summarize, anywhere between 8 to 12 for bioreactors. It is quite standard for anaerobic. However, the concentrations can be a bit higher, so in the range of 10 to 15 grams per liter.
Okay, thank you. Elena, another question for you. Can the effluent from the anaerobic MBR be polished directly with reverse osmosis?
Yes, yes, absolutely. In fact, we have some projects where they are specifically doing this, and well, the permit for the effluent from the anaerobic MBR is always having SDI less than 3. COD concentration is pretty low, so there is not a problem with that. And we have some cases where reverse osmosis is performing very, very well with high recoveries and no problems. In fact, I would say that even we have cases which in let's say worse conditions, such as the treating of digestate, where ultrafiltration membranes are used for the direct filtration of digestate, so that permate is still having a significant amount of soluble COD and other components. And in these cases, our customers are also applying reverse osmosis directly after the ultrafiltration. Having said this, you need to be careful when designing the reverse osmosis, selecting the proper RO module, but this is something that can be done and operated very, very efficiently.
Okay. Okay, thank you. Another question for Elena. What is the standard cleaning procedure?
Well, a standard is, I would say it is similar to other type of UF membrane. So usually it is alkaline procedure for removing mainly the organic fouling. This is normally the first stage. It combines sodium hydroxide in general with a pH up to 11 with oxidants, usually hypochlorite with 250 ppm. And then the acid step, which is quite frequently applied with based on citric acid. You can use other acids, but citric is frequently the preferred option. And then, of course, in many cases, commercial membrane cleaners are used. They are in general, or they can be a bit more efficient, maybe not only or maybe not dealing with permeability recovery, but usually they are making everything quicker. It is well, you require shorter cleaning times with them. And of course, if it is an oil-water separation applications, for example, applying some kind of a degreasing booster is also helping a lot. And in some cases, yeah, enzymatic cleaners, these kind of specific products, we have seen many cases where they are really making a difference.
Right, okay, thank you. Moving on to the next question. Elena, what is the range of cross-flow velocity and transmembrane pressure applied?
Okay, for the cross-flow velocity, let's focus first on the standard cross-flow operation. This is usually operated between 3 and 4 meters per second. Transmembrane pressure, let's say average values can go from 1.5 to 3 bar, something like that, maximum. Then, as I was mentioning before, in the eco approach, where we design with low cross-flow velocity and obviously with lower fluxes, cross-flow velocity can be between 1.5 to 2.5 meters per second. In this range, let's say 2 meters per second.
Right, okay, thank you. I think we have another question, Elena, for you again. What is the FOG, the FOG limit that is allowed for membranes? The question is related to the dairy industry and the mention that the chemicals in DAF were too high. So how the membranes changed that?
Okay. Well, first, as I was mentioning, tubular ultrafiltration membranes per se are not affected by oil and grease. We have projects where we are really separating oil from water, let's say bilge water treatment, these kind of applications. So there is not a problem with the oil. And the maximum concentration can be, as I was mentioning, more than 100 grams per liter. The limit, let's say, in oil-water separation is the transition between the oil in water situation to water in oil. In this moment, oil will start passing through the membranes, but this means it is more or less approximately at 35% 40 oil concentration. In the case of this anaerobic MBR referencing butter treatment, why was the chemicals addition to the DAF stopped? This is mainly because they implemented the anaerobic MBR, okay? So, as I was mentioning, the main impact of oil and grease is in the, or when we need to be a bit more careful, is in the aerobic MBR, but not because of the membranes, because of the biological process. In the case of anaerobic MBR, you can feed the oil, and this is very good because you are transforming more organic matter into biogas, and especially fats, oil and grease are a very good ingredient, let's say, for producing high quality biogas. The only thing that we need to, or we recommend to remove is the free oil, okay? So when they implemented the anaerobic MBR, the oil corresponding to the high loaded streams was directed to the anaerobic MBR. So in the DAF, only maintaining the aeration without chemicals, this was enough for feeding the aerobic MBR.
Okay, perfect. Thank you. Yeah, I think we have one more question, and concerning the time, we have time for that. So let's say this is the last question. How do you select the concentration factor for selecting the fleet flow? Adrian or Elena?
Adrian?
You can go ahead with this one. It's more the
Okay.
technical side. No problem. I can also.
Okay. Now, well, this depends also a bit on the application. If we think on aerobic or anaerobic MBR, the concentration factor, first we consider the MLSS concentration. So we usually select a concentration factor between 1.1, 1.25, let's say. If MLSS is low, let's see, for example, for us, what is low? It can be 8, 10 grams per liter, MLSS concentration. The concentration factor will be 1.2. If it is higher, we could go to 1.15, and in very, very high MLSS concentration, let's think on 20 grams per liter, which is not the most usual, but it happens in some cases, we could go to 1.1. This is for MBR and anaerobic MBR. For direct filtration, this is a different topic because in direct filtration, we can have what we call direct reject. So we are feeding, let's say, 10 cubics per hour, permate is 8, and reject is directly discharged, 2 cubics per hour. So the concentration factor is the one corresponding to the global process. In this case, it would be 5. In other cases, when we operate with semi-continuous reject, we usually apply a concentration factor in the range of 1.5 for providing the system with flexibility in terms of permit production. So it can be between 1.1, 1.5, and in the case of direct reject, this concentration factor comes directly from the global mass balance.
Great. Good. Okay.
And I write, so sorry, Elizabeth, last question from Adrian for the scenario number 6. How do you handle the precipitate in this scenario? I presume he refers to the potential scaling, I don't know, or if it is the precipitates that come from the previous precipitation process.
Yeah, I think what I understand, perhaps to highlight here is that it is important that the chemical treatment before, or the physiochemical treatment where there is a precipitation of the solids before the ultrafiltration, it is also properly designed, so there is enough time retention for them to precipitate. So there is well mixing of this feed tank used before the ultrafiltration, and normally we also operate with an intermediate tank between the chemical tank and the ultrafiltration. So there will be the chemical precipitation tank, which is well designed for mixing and retention time. Then there is the feed tank before the ultrafiltration. So if I understand correctly, that is the way to handle this precipitate.
Mm-hmm. And I would add that providing that the precipitation is performing well, this kind of applications where you have mainly inorganic precipitates plus clean water, the filtration performance is very, very good. High fluxes, very low fouling. So when everything is working properly, the ultrafiltration system behaves highly, highly efficiently.
Okay. Thanks for your answers. I think we can end the questions and answer session. So I hope everyone that had questions that they've been answered. Yeah, let's go to the last slide concerning the time, obviously, as well. So yeah, so if you had a question that we were not able to discuss, or if you need more information, whether it is technical information or information on references and case studies, or if you want to discuss your potential projects, or perhaps you're interested in renting a pilot unit for an on-site demonstration, please get in touch with us. Our contact details are listed right here in this slide. I also can say subscribe to our newsletter and follow our LinkedIn page to stay tuned for our latest news and upcoming events. And I want to thank both our speakers, Elena and Adrian, for sharing your expertise today. And thank you all to you for attending and participating in this workshop. We hope you found this session valuable, and we look forward to connecting with you in the near future. So wishing you all a great day, and the workshop will end now.
Thanks, Elizabeth, and
Thank you.
Thank you to all the people joining us. Bye-bye. Have a nice day.
Bye.